In battery charging, one complication that comes uh, up very often is so-called electrolysis. Electrolysis, especially of the electrolyte material. For secondary battery, the charging voltage, as what we learned, has to be larger than equilibrium in order to drive the current in reverse direction. Here, for example, we show the lead acid battery, the electrode potential for both the negative electrode and for the positive electrode versus the charging time or state of charge. The bottom one is for the overall cell voltage. The top one shows the electrode voltage for the more positive electrode and for the more negative electrode. And for the more negative electrode, as what we learned before, the electrode reaction is actually between lead and the lead sulfate, while for the more positive electrode, the electrode reaction is between lead oxide and the lead sulfate. Okay, and then at zero charge time or state of charge, the voltage is relatively low. On the other hand, in order to drive the um, reaction in reverse, drive this overall um, drive this overall reverse reaction or full cell reaction, we have to apply a voltage higher than the equilibrium, and how high it depends on the um, current density that we want to use during the charging process. And as you can see, with increasing charging time or state of charge, the overall applied voltage gradually increase. Initially, rapidly and then relatively stable, but quite slight increase. And then at at a certain moment, the voltage applied becomes too high. For example, in this case, around 2.4 volt. And this is when the situation would occur that gassing would start to happen. What is gassing? Gassing is essentially we are so much higher than the electrochemical stability window for water. Remember, the water and the electrochemical window is only around 1.29, but with large enough overpotential, let's say the overall applied voltage is 2.4 volt, and for water 1.29 volt 229 volt, we would now have more than 1 volt of overpotential, and that would be able to drive the water splitting. At the negative electrode, we are reducing the trace amount of proton to form hydrogen gas, while on the positive electrode, we are stripping the water of electron to form oxygen gas. So that is the source of the gassing. Hydrogen come out, oxygen come out, essentially water electrolysis reaction, as we apply larger and larger potential in order to do the charging of the battery. When the voltage goes beyond certain level, at one time the battery still got charged, but at the same time there might be the issue of gassing due to water electrolysis. And then, of course, this will continue until the complete of charging, but during this process, a lot of water also got consumed to form oxygen gas and the hydrogen gas. Okay, so this is what we said. To make charging, why do you do this? Because we said in order to maintain the charging at an adequately fast rate, we have to apply voltage higher than equilibrium, and how high depends on the current density. But no matter what, you'll be higher than the equilibrium, and as you the charge it more and more, the equilibrium potential also increases, and you have to apply even larger voltage, and at a certain moment the applied voltage is enough to drive appreciable amount of side reaction. For example, electrolysis of the electrolyte, and in this process, um, we would have gassing issue, side reaction that is introduced due to excessive amount of over potential applied over compared with equilibrium for the electrolyte such as water. Okay, that will be a one major complication when we do the charging process for a battery. You apply the voltage, and the applied voltage may exceed the stability electrochemical window for the electrolyte used by a lot, and in this case the equilibrium for water is around 1.229 volt as we said, and when you apply 2.4 the over potential may be over 1.1 volt, and that is enough to drive appreciable amount of side reaction, which is water electrolysis, forming oxygen gas and hydrogen gas. Okay.